So good morning, my name is Qiaomin, and I'm so delighted to share a part of my research here with you today. And in order to show you the latest research progress in my PhD, I have changed my title to Integrating the Simulation Models to Improve Prediction of Crop Change from Geo-based multispectral data using deep learning. And the research objective is try to improve the crop characterization with the aim of digital technologies, and the high throughput phenotyping is one of the most promising technology that we can use in agriculture today. And the high throughput phenotyping means the use of the proximate sensor and the imaging technologies to for the phenotype measurement. And nowadays we have a lot of platforms can be used to do the high throughput phenotyping, from the ground-based robots to the satellite. And the general application pipeline for the high throughput phenotyping is like this. We use the sensor mounted on different platforms to collect the sensing data, which can describe the crop growth status. And then we try to extract the crop change from the sensing data. And in this process, we will need a predictive model that describes a signal chain relationship, so that we can input the sensing data into this model to predict the crop traits that we are interested in. So now the question comes to how can we create such a predictive model or such a relationship? The conventional ways like this, we use the measure crop trait or the observed sensing data to build an empirical relationship. But the problem is such a relationship generally site-specific. That means it can be applied to a wider situations that is quite different to the environment that used for collecting the data to build this relationship. So what we are thinking about is try to generate a more general relationship that can be used to wider environments. The good thing is that we know this process from the sensing data to the crop trait, or from the crop trait to the sensing data, can be described using the radioactive transfer model. So if we integrate the radioactive transfer model to the high throughput phenotyping, we can create a more general relationship in two ways. The first way is we can just use the cause-effect relationship built in the radioactive transfer model, so that we can just back calculate. Yes, I can't use this one. Okay, we can just back calculate the crop trait from the canopy reference data. Or the second way is we can just use the radioactive transfer model to simulate a synthetic data set, and then we can rebuild a relationship from this synthetic data set. And compared to the collection of the measure of the collection of the experimental data, is quite easy to generate a synthetic data set that can represent the diverse growth and observation conditions. But the problem is we cannot consider the biological control among the crop trait in the traditional way to generate a synthetic data set. So here I will try to propose a conceptual framework to introduce the biological control in the synthetic data set in order to build a more powerful predictive model. So here is the framework. And in this part, that's the traditional way to use the radioactive sensor model to generate synthetic data set and build a predictive model based on this synthetic data set. But in our work, what we did is try to use the crop growth model to inform the input variables of this radioactive transfer model. And this is realized by converting the output variables of the crop growth model as the input variables of the radioactive transfer model, so that we can just generate the input variable of the radioactive transfer model that are constant to the crop growth biology defined in the crop growth model, and then we can have the better radioactive the better canopy reflectance that better reflect the real canopy status, and then we will have the more accurate and stable prediction. That's our final objective. So what's the main difference between these two synthetic data sets with and without biological constraint? The main difference lies in the combination of the input variables of the radioactive sensor model. For that synthetic data set without the biological constraint, the input variables of the radioactive sensor model are combined randomly. But for that data set with biological constraint, the input variables are combined constrained by the biology defined in the crop growth model. So here I will show you example for these two data sets. Like here, this figure shows the spatial co-distribution of the LAI and the leaf coffee content. So the black point shows the combination of these two crop traits in the dataset without constraint, while the red points indicate the combinations of these two crop traits in the dataset with biological constraints. So we can see introducing the biological constraint can potentially remove those combinations that cannot exist in the real crop growth status defined by the crop growth model. So here, in order to highlight the potentials or advantage of adding the biological constraint in the synthetic data set, I train two predictive models based on the synthetic training data, and one model using the data set without the constraint, and another one using the data set with the constraint. And both of these models are using the 5-band reflectance to predict 4 crop traits simultaneously. And then I will test these models on the synthetic test set to see their theoretical performance. And then I've also tried to validate our models on the field experimental data. And this figure shows the field design of the this field experiment conducted in 2006. And from this figure, we can see there are this field experiment included multiple genotypes and different management practices so that it can generate contrasting canopies that can be used to validate our model. So now here's the theoretical performance of the predictive model on the synthetic test set, and the x-axis shows the null value of the crop trait, while the y-axis shows the predictive value of the crop trait. So for each figure pair, the left one shows the model performance without the constraint, while the right one shows the model performance with constraint. And we can see adding the biological constraint can improve the estimation accuracy and stability. And for the estimation of leaf coffee content, we can see adding biological constraint can enable the leaf water content to be estimated using the band reflectance in this visible to near-infrared range. But actually, there's no effective information to be used to extract the leaf water content in this range. And here is the practical performance. And we can see it's quite hard to reproduce the accurate prediction on the theoretical data set when tested this model on the real data, but we can still see the advantage of adding the biological constraint because the model without constraint failed to estimate the leaf water content, but the model with constraint enabled the leaf water content to be estimated. So here we can have the Steve findings, and the first one is adding the biological constraint among relative variables enabled the prediction based on the relationship between the crop trait and sensing data, as well as based on the association among the crop trait themselves. And then if we add in this biological constraint, association can substantially improve the prediction accuracy and also enable some crop trait to be estimated from the range without effective information included. So if we want to know more about this, our research can just have a look at our research paper just published this year in JSB. And the field experiment we conducted in 2006 was funded by GIDC, and I would like to thank our China Scholarship Council and UQ and SARO for providing financial support in my PhD. And I also want to thank my supervisors and my colleagues for giving me advice in this work and this presentation. Thank you.